My name is Kurt. I'm a product manager at Google. I work on the healthcare and life science team, and I focus on Cloud Healthcare API. We're very lucky today to be joined by David from Stratus Medicine, CEO. He'll be speaking in a little bit. And let me also say, actually, before we jump in, I must freely admit, we were just talking about this. When David and I saw that we were at the 5 p.m. slot and not in the main venue, we were more than a little concerned that no one would show up. So I just want to thank everyone from the bottom of my heart for not forcing us to stand up here and talk to an empty room. So thank you. In today's session, we're going to be talking about three things. In the first bit, I'm going to focus on the role that Cloud Healthcare API has in healthcare infrastructure to approach, again, serverless machine learning. I'll then talk about a general solution architecture that we use and we take with customers who are looking to implement a similar solution. And then I'm going to hand over to David, who's going to talk about, with a heavy dose of pragmatism and insight from the field, what this looks like in a real deployment. So let's get started. I think it's useful in healthcare to help contextualize conversations about caring for patients, working with providers, in the context of, in this case, a nurse. So this is Christy. She's formerly an ICU nurse, currently a nurse practitioner. And those of you in the front row here may notice that Christy bears a striking resemblance to me. It's a keen observation. Christy is, in fact, my little sister. Aww. Now, the reason I mention that is Christy and I have this little game we play of one-upsmanship at family gatherings and such, where she tells me all the things that she's seen in clinical settings, and I try and counter with all the things I've seen in healthcare IT. And needless to say, Christy, again, ICU, rolling inside and out of the ED, Christy has seen things, and Christy usually wins. But I asked her, hey, I'm going to be giving this talk. I'm going to be talking about data-driven problems. Can you give me some examples where you think there ought to be more data in the EHR, your medical record system, and you just can't quite find it at the moment you need to make a decision? And she looked at me and sort of said, whoa, sighed. Where do you even want to start? And I mean, when all of us in this room who are familiar with healthcare IT and clinical decision support, cognitive assistance, you quickly realize there is an abundance of opportunity here. There are thousands of problems that need to be solved. And let me give you a couple examples. In this case, assume there's a small inpatient clinic, relatively rural. It doesn't have a lot of specialists, or to the extent it does, they only visit once a week. And this is problematic because if a patient is admitted, gets their usual labs, and it shows an elevated troponin. Troponin is an early indicator for cardiac arrest. The question is, that doesn't always happen. So should you refer this patient from this rural care facility to a larger care facility that has cardiac specialists? I don't know. Let me give you another example. Assume a patient just suffered from a cerebrovascular accident. They had a stroke. So they're laying in the bed, just recovering. One physician says, oh, we need to keep the blood pressure up. We need to basically soak the brain in blood, oxygen-rich blood, help it recover. Another physician says, no, look at this CT scan. Look at that, see that bulge by the heart? If we keep the blood pressure up, we're going to shear the aorta. What do? What should the blood pressure be? Right? These are just two examples of the myriad of problems that exist in clinical decision-making. And the question is there data, or is there a process to sift through the data and arrive at a support and a solution that can augment and extend the clinician? And I want to touch on a paper. This was a paper actually presented when we introduced Healthcare API last year at Next. I mentioned this paper because at the time it had just come out. This is a paper from our Google AI team, and it shows, among other things, that first of all, you can map a bunch of data to FHIR. I'll come back to that in a second. But secondarily, it shows that having mapped your data to FHIR, you could make highly sensitive and specific predictions for adverse clinical outcomes. So again, I mentioned that last year. Since last year, we've been working with customers and partners to start to bring these tools into clinical workflow. One of those examples I've highlighted here, this one's public, so again, not disclosing anything that's not already public, but this is with a partnership we worked with Emory Institution in the United States, where they had an issue with bloodborne infection in their ICU, so sepsis. Now, there are a lot of algorithms out there for addressing sepsis, but they had a particular set of conditions that meant they needed to build a model. This team saw the work and saw TensorFlow and said, hey, could I build a pipeline like that? Could I ingest my labs and vitals? Could I deploy a solution? And in fact, they did. And not only did they do it, they then won a grant from the HHS, Health and Human Services, to expand the program. This is great because it shows that this pipeline is actually feasible in real clinical settings. So with that in mind, right, so I've set up the problem. I've now described why are we even approaching this problem, why are we building what we're building, and I think this is where I want to shift into talking about Cloud Healthcare API. And I think a lot of people who approach data science, and especially data science in medicine, you go into it with this mindset that there are these 3 phases, right? These are common to any data science project: discovery, model training, model deployment. The question is, for people who are newer, are these equal in time? Most people who are, again, new to the field say, oh yeah, sure, I'll just do some discovery, I'll train a model and deploy it. And these are not equal in time. In fact, most of us in this room who have lived this experience know that we spend an enormous amount of time and energy in that first spot, in discovery. Training turns out to be the easy part. Training turns out to be the part that goes fast. And then there's deployment. Yeah, there's a lot of issues around patient safety and security of the data, but at the end of the day, it still pales in comparison to the amount of time we're spending in discovery. I'll put this problem a slightly different way. On the one hand, you've got all these clinical systems that institutions have been investing in for the last 10, 20, 30 years. And you've got them over here. They're largely on-prem. Over here, you've got this thing called cloud. Now, cloud is fabulous. Clouds where we got TensorFlow at scale. Clouds where we've got chips designed to run TensorFlow. Clouds where we have BigQuery running. But there's this enormous gulf between these 2 worlds, because you can't just rip these systems out and move them to cloud. So the question is, how do we fill that gap? And that's the role of the Healthcare API. The whole purpose of the Healthcare API is to help bridge these existing systems with the capabilities of Google Cloud. And in particular, and I like to emphasize this point because it's often lost in these discussions, at the end of the day, we see an important step in deploying Healthcare API is that we need to necessarily speak and support the formats and protocols that are already native to the industry, data that these institutions already have, they're already generating. Because if we can speak these formats and protocols, we can bring this data into Google and into cloud. Specifically, and again, this touches on our particular topic today and our specific use case, we want to apply a variety of analytics and machine learning services to this data, which again, the role of Healthcare API is to facilitate that integration. Now briefly, I just want to touch on this to answer the question. We get a lot of questions about, well, where does this fit in the Google product roadmap in terms of platform as a service? Is it Gmail, right, fully managed by Google, SaaS? Is it raw infrastructure, raw cloud, VMs, and so forth on Compute Engine? And it really sits in the middle. It shouldn't really matter from your perspective if you're throwing 1 resource in, 100 million resources in, 1 DICOM image, 100 million DICOM images. It should scale transparently for you. That's our goal. Now, from an API perspective, we call it Cloud Healthcare API because it's very much an API surface. You have this hierarchy of your project, right? You control the project. Within your project, you specify a location. This is critical in healthcare because that informs the API for where to store data for the rest of that path. You create a data set. A data set is a grouping of multiple modalities of data. So you can have imaging data over here, and FHIR data here, and V2 data over here for clinical messaging. And finally, you have your stores, right? Stores implement the modality-specific API. And I emphasize the point that it's an API because if you're building an application, you're just addressing an API in a very familiar way. This is no different than any other API you interact with. The key difference is that under the hood, it's scaling and implementing these specific modality data types for healthcare. And of course, I would be remiss. I don't want to spend too much belabor the point. We have entire sessions on this topic, but I do want to emphasize this whole architecture is designed to support the storage of protected health information. So yes, it is covered by our business associates agreement. Okay, now, I love this slide. And every time I show this slide, people are like, oh, it's so boring, Kurt, why do you put this in your decks? And I like it a lot because what it shows in 4 commands, let me explain what's going on in this example here. But in these 4 examples, it shows, oh, we created a data set using gcloud, our CLI. We've created a V2 store for clinical messages. We've created a DICOM store for clinical imagery. And we've created a FHIR store for FHIR data. And we did this in 4 commands. And it doesn't matter. Again, you can send it 1 image, 100,000 images. I take the fact that it's boring as a compliment. We have made the ability to create this infrastructure so boring that this is the trivial part of the process. And that's great. The more and more we can make this type of work mundane, the more time developer teams that we work with can spend in the application space, helping patients, helping providers. And that's where the value is going to come from. And briefly, I just want to cover some of the configuration options. These end up to be useful, and you'll see why as I start to talk about the solution architecture. But in this particular case, when we're talking about an HL7v2 store, there's one configuration option for segment terminators. I don't want to spend too much time on that, but for those who have deployed V2 in the field, know that you can configure that in a V2 store. The piece I want to mention explicitly here is that every single store in Cloud Healthcare API can be associated with a pub subtopic. This becomes important. I'll get to this in a minute. DICOM, same idea. It can be associated with a pub subtopic. Every time a new image is sent to a DICOM store, it generates a notification saying, hey, I got a new image. Same thing with FHIR. You look at a FHIR store. FHIR, we have a number of parameters that we support for various. FHIR is a very complex spec, so I don't want to dwell on the spec itself. But the things when you're looking at the FHIR specification, know that the different parameters that are in the spec can be tuned via configuration on the store. Again, the important point that I want to emphasize for our discussion today is the fact that you can associate a pub subtopic with the store. So what do I mean by that? Again, you have your healthcare store. It stores healthcare-specific data. When data is written, when data changes, generates a notification to Cloud Pub Sub. That triggers a series of notifications that any number of applications that you build can be subscribed to. And from there, this is an example of what that message looks like. So it's just like any other pub sub message, namely there's a data element that's base64 encoded, like all pub sub messages on Google Cloud. That contains the path of the resource that changed. So any subscribed application can grab the data that changed. This will become an essential point in a second. Now, I emphasized earlier that it's just an API. So to get data in and out, you simply call the API. In this particular case, we have a sample resource. We're going to pull it out for some application. That's great. Now, this is where things get interesting. I said at the beginning, one of the key roles of Cloud Healthcare API is the ability to export data and project it from its native data type to BigQuery so you can run SQL-based analysis against it. That, again, is just an API method. You invoke on the store, say, hey, take this FHIR data, project it to BigQuery. Take this DICOM data, project the metadata to BigQuery. And that, under the hood, will trigger a job that we project that to your own BigQuery store. For the case of FHIR, there's a community-supported specification for an analytical schema. We implement this specification. So to the extent possible, this is an important point, we are implementing industry standard specifications on Google Cloud technology. So again, the projection is based on this schema. And to trigger it, you just set an additional parameter highlighted in blue on this slide to say, I want my projection to follow the analytical schema based on the community spec. Last point I want to make about interacting with a FHIR store is that all of these FHIR stores, rather, can export and import directly to BigQuery. I actually should have mentioned this point earlier. They can export and import to BigQuery and be connected to your business intelligence tools. So you've got R, you've got Tableau, you've got all these services that you're used to running. They can interact directly with that projected data. So you don't have to teach your data science team to use a different tool to connect to the projected data. This is the point I was trying to make. When you're ready to export your data for the purpose of training a model, we have a convenient API call that lets you say, hey, store, take all my data and drop it into BigQuery. And you can see, again, through a single API call, that that method will take your data, whether it's a DICOM data or V2 data or FHIR data, export it to cloud storage, in this particular case, so you can train the model, or in case you want to move it back on-prem, or take it from on-prem and shove it into the Cloud Healthcare API. All of this is possible as an API method. Now, last point I want to make before we dive into the solution architecture is to talk about the fact that it's in beta, finally, yay. Over the last year, one point of emphasis has been performance. One point of emphasis has been conformance. So those are the two things that our team is largely focused on. And again, I mentioned this before, it's in scope for the BAA, and importantly, for our term service. Okay, so I've set the stage for why Cloud Healthcare API. I want to spend a little bit of time now talking through the architecture for how we help these teams deploy a solution, which sets the pattern that you'll see repeated when David speaks about his particular implementation. So before I dive into that, there is one essential point I'd like to make because this is a recurring theme as we talk about these implementations, and that is namely the focus on FHIR. So FHIR serves two important roles in our approach, and that is namely, it's a very extensible data model, which is incredibly convenient. The second is that it's a graph, so any graph-based querying and technology used can work against FHIR data. And then third is actually the fact that it's also an API specification. So you can use it as a transactional target in addition to being the target for labeling and training data. Also, this actually came out last week. CMS announced that they're transitioning some of their services over the next few years, not immediately, but the initial wave, the demo, was released last week, so you can actually extract claims data in FHIR bulk format. For those of you who are paying attention to the regulatory environment during HIMSS, you probably also noticed that both CMS and ONC released proposed rules with a very heavy emphasis on exposing APIs. The ONC rule, 700 pages, mentioned FHIR a little over 300 times, right? So there's a clear both data science reason to be taking this approach and a clear push from the regulatory environment to say, maybe this is something worth investigating further. For the purpose of our conversation today, I'm going to talk about a very specific implementation, and that is something called CDS hooks. In the clinical space, CDS hook is one implementation of clinical decision support. There are, of course, many. Best practice alerts, flow sheet integrations, ClinKB integrations. The point is, there are a lot of disparate integrations that are possible. I'm going to focus on this pattern because I want to set up the discussion for what you'll see when David presents his work. But a CDS hook is fundamentally no more than a webhook. So it triggers an alert, an event occurs inside a care facility, that triggers an alert just like any other webhook you're used to. Now, in the case of a CDS hook, there are a number of events that trigger that. Patient view is the most commonly implemented to the extent CDS hooks are implemented, but there's others. When an order was reviewed, a medication prescribed, the order select and down, which I've put in gray, those are technically in the spec. We haven't seen them widely implemented, but I mentioned them in the interest of thoroughness. Now, the CDS hook service is in turn expected to respond with a payload that's designed to trigger a native rendering in the source EHR. So in the case of Cerner, there's a specific UI element that gets rendered when this webhook is answered. So this gives you, at least for the purpose of our discussion, a target when we're talking about an architecture for delivering clinical decision support, cognitive assistance into workflow. The other convenient property about it, which I like for discussion and developer purposes, is that there's an open sandbox. So you could leave the session, go test it on the sandbox that's developed by Cerner. So Cerner is one of the larger EHR vendors in the world. They have a process to just test these locally. Again, convenient when you're doing development activities. So let's return to the three phases I set up at the beginning. You have discovery, you have training, and you have deployment. In the case of discovery, we actually spent a lot of time on this already, right? I talked about the ability to project data from the healthcare API to BigQuery. So you're ingesting these V2 messages, you're ingesting this FHIR data, this DICOM data, and you want to project it for the purpose of discovering what are some abnormalities in my data. Connect your R process to do some sifting around, oh, do I have some biases expressed because of my collection procedures, right? All of that work is enabled through your projection into BigQuery. For training, this is another area which I'll point you to some open source work that our friends at Google AI have performed. There's a whole step-by-step process we've identified, which is, again, we've tested a number of scenarios, but the idea is how do we take FHIR data, how do we label it, annotate it, and then how do we train a model? This has a step-by-step guide on how you would do that after exporting the data. And the basic flow, which I'll cover for the purpose of when you're deploying it on cloud, is you take your FHIR data, you export it to GCS, you then label it however you see fit using, again, the tools that I just showed on the last slide, and you create a model which you can upload to ML Engine. Now, the nice thing about the work that the AI team showed on the last slide was that that also works locally. So if you're looking to develop this kind of tooling, you can test it directly on your machine. Now, in terms of deployment, what we're largely talking about is, okay, how do we implement this CDS hook? How are we going to build a solution that pieces together various parts of cloud in a way that answers that webhook request? So in this particular case, I've used the Kubernetes engine logo for this EHR relay, and that's because you're going to be ingesting clinical data somehow. And I say somehow because for the purpose of our example, what we want is a stream of FHIR observations. We all know there are very few EHR systems streaming FHIR observations today. What you're realistically getting is an HL7v2 message streaming labs and vitals. In this case, I used an ORU for an example. So the question is, okay, great. Now, how do I turn that into a FHIR observation? There is some work on our side for ingesting HL7v2 message. This is an open source project that speaks MLLP, so minimum lower layer protocol is the protocol necessary to ingest V2 messages. We have an open source container that you can run on Kubernetes engine. That's why I used the Kubernetes engine logo earlier, to ingest these clinical messages. Now, we also work with partners. So you may have interface engines in your institution today that are capable of directly integrating with Cloud Healthcare API. One of them, this is a team we work with, built an integration for Mirth, or NextGen, to ingest V2 messages directly from an existing Mirth installation, so that a system that already invested in Mirth /NextGen could easily connect their data to cloud. So somehow, some way, using either of those services or one of your existing interface engines, you're streaming V2 messages to Cloud Healthcare API. Now, I mentioned earlier that it's connected to PubSub, and this is the essential feature, because now you have a mechanism to know when new data was written to your V2 store. And because you have a mechanism to know that, you can ultimately trigger data flow, again, either directly or this is an area of investment for our team, or how can we make this more of a managed service, but that maps that V2 data, grabs the message, and turns it into a FHIR observation, right? So this is the target. Somehow you have this little engine running that's mapping V2 messages to FHIR on a real-time basis. So we go back to the example where let's assume for the sake of argument and for the sake of my diagram that we're streaming observations from a source, which may be this data flow process under the hood. Now we'll go back to the notification idea. So now you've got these FHIR observations being written to the store. Again, you can lean on the fact that PubSub is sending out notifications about this new data. So your Cloud Function can directly attach. And why is Cloud Function necessary here? Well, because somehow you need to invoke the model with the right FHIR data. So because the PubSub notification contained information about what FHIR resource was mutated, it can grab the patient everything bundle from the Healthcare API, which effectively is a representation, everything about that data, and send it off to ML Engine for a prediction. Once it receives that prediction, it can then generate a risk assessment and write the risk assessment back to the FHIR store. So now you've got this pipeline of your ingesting data. The model that you trained in phase 2 is running on ML Engine, looking at the patient everything bundle, which you, again, trained using a TensorFlow sequence example, and it's generating a prediction, which you're converting into a risk assessment. So that whole process is running asynchronously, right? That's, as new data is streaming in, that whole engine is churning. But now you've got the CDS hook component, because the hospital says, oh, I have a new patient, or a clinician looks at a patient. That triggers a notification to a Cloud Function, because for those familiar with Cloud Functions, one of the triggers you can use is an HTTPS invocation. So now it's, oh, I got a webhook request from this hospital. I know how to handle this. Let me reach out to the Cloud Healthcare API, grab the risk assessment, and format my payload. Now, I skipped over the fact that CDS hook has an authentication authorization step, but that's in there. That would be in your business logic for the Cloud Function. But what you're generating here is now you've got that asynchronous loop running, generating risk assessments, and a synchronous loop to inspect the data and generate a response for the care facility in the immediate workflow. Again, I want to point of emphasis, we have an open source project that shows how that pipeline is built. This project actually also has a UI, though I want to caution people. What this demo does is it says, I'm going to go to country X. Do I need an immunization? That is not a great problem for machine learning. Freely admit that. And the reason is, because if you're going to go to country X, you would simply consult your relevant authority and get your appropriate immunizations. You don't really want to predict that. But the underlying pipeline is the same. And so we wanted to pick a topic where it was clear that the pipeline is feasible to show you how all the pieces fit together, even if the problem space, should you or should not get an immunization, is relatively trivial. That pipeline is consistent across all the implementations of the solution that we've seen. Also, for imaging data, I have focused on FHIR and clinical data for the purpose of this discussion, but there's a code lab also available on GitHub for running this exact same flow, except using imaging data. So again, whether you're using streaming clinical data or data from an EHR, you have a consistent system and architecture to apply that's able to generate these sensitive and specific predictions. And with that, I want to hand over to David, who's going to talk about this in practice.
Fantastic. Thanks, Kurt. Hi, my name's David Burdick, and I'm the CEO of Stratus Medicine. At Stratus Medicine, we partner with health systems to help them accelerate their innovation programs. We leverage technology and data science to really make impact in healthcare. And I'm going to talk to you today about a case study where we've actually applied these healthcare API tools. So like I mentioned, we apply technology and data science to healthcare, and we've worked with both internal innovation teams and external vendors. And we're leveraging medical records and genomics, images, and machine learning methods to really impact clinical care, clinical decision support, health system administration. And what we've seen frequently is that innovators in this space don't have access to the tools that would really accelerate their workflows. It's oftentimes relative to data security, data use, and privacy, which are all very important things. So how can we help healthcare IT move to the cloud? Right now, they're in this world of virtual machines. They've built a nice security workflow. It works for them. The boundaries are well defined. But they can't incrementally move towards infrastructure as a service or platform as a service where there's a lot of value, because ad hoc use is risky. You're not going to turn your developers loose with an API key. And in fact, when you do, you get things like the data breach at UW Medicine this spring, which I was involved in. Well, my name was involved in. where somebody just put about a million patients worth of data into an unsecured cloud bucket and Google indexed it. So, it's expensive for IT to productize what the public clouds have created, and it's hard for them to support new trends like serverless or Kubernetes. And so our viewpoint is that you really want healthcare to jump from the VM, Gen 2 computing world to a software as a service product that wraps up the public cloud offerings into kind of an opinionated workflow that's specifically tailored to healthcare and healthcare application deployment. So now what we can help health systems do is create a secure workflow for application development and deployment, enforce security best practices, do active breach prevention, and because a lot of health systems don't want to hire data scientists and software engineers in-house, we can provide professional services for that. So if we stand on the shoulders of the public clouds with their infrastructure and platform as a service, and we narrow that down to a specific SaaS offering, then we can focus on applications that provide real clinical value. And we want the teams building those to be able to iterate quickly and not do it with specialized skills. So let's talk more about how we can do innovation with these modern tools and specifically clinical decision support. So for the last 5 years, we have been a strategic partner of the Sun Yat-sen Cancer Center in Taiwan. They're one of the premier cancer centers in Asia. They have a 325-bed hospital that provides both inpatient and outpatient oncology care. And what's really interesting is they have been operating profitable bundled payment for over 18 years. These are 5-year-long episodes of care. And in doing that, their outcomes are as good or better than top US institutions. In doing that, they've seen what the keys to success are in the value-based care world. They need to leverage data appropriately, have really good care management, and effective use of their resources, both in terms of what treatments they use and the use of their staff. So the case study that we're going to talk about is distant metastasis in breast cancer. So distant metastasis is when a breast cancer spreads to other organs. And the typical progression goes like this. You have the initial adjuvant treatment, so that is your first-line treatment. And then in some patients, unfortunately, the cancer spreads to other organs. There's a regimented follow-up, so every 3 months initially, then 6 months. But unfortunately, there's this kind of problem here where the cancer spreads, but the patient might come into the clinic before a regularly scheduled follow-up with some symptoms. And are those symptoms related to a recurrence, or are they just pneumonia or some other comorbidity? So it's up to the physician's discretion to say, well, should I use advanced imaging, right? This expensive and invasive imaging, maybe a chest X-ray, and determine, is this related to their breast cancer that they had 4 years ago, or is this just something else? So how do we help physicians make that decision, and how do we standardize that across the different medical oncologists in the group? So the goal here is to create kind of the earliest identification of recurrence and follow-up, and we'll create a model that stratifies the risk of recurrence for each individual patient, with the result being that we have effective and efficient use of advanced imaging, and we can reduce by 3 to 6 months the time from the actual cancer recurrence to startment of recurrence treatment. So generically, the process looks like this. We have a DICOM store for images, we leverage FHIR for modeling the medical record, and we use registries for curated parts of the medical record. We take these 3 data sources, feed them into a machine learning framework, and bring actionable insight to the clinician. Let's focus a little bit on FHIR and registries. So like I said, we're going to model the entire medical record in FHIR here. And then we'll use the registries that are extracted from that medical record to be a specific clinical area. So in breast cancer, this would be, what are the patient demographics? What is the pathologic staging for that tumor? What was the initial adjuvant treatment? And then what is their stage of recurrence, right? Have they had a local regional recurrence? Have they had a distant metastasis? These registries are super valuable to the Sun Yat-sen. They use them for retrospective analysis and things like SAS and Tableau. They use them for training models, and they use them for billing, because when you're in a value-based care reimbursement program, you need to use kind of these deep pieces of the medical record in your billing. So what is FHIR? Probably most people are familiar with it, but if you're not, it is an HL7 specification that both models medical records data and also provides an API. It's a directed graph of resources, and these resources are things like the patient, practitioner, diagnostic report, medication prescription. And FHIR means a lot of things to different people. It's a young spec, less than a decade, and it was originally built for health information exchange. So some people view it as health system to health system. A lot of people with Apple's entrance to the market view it as a direct-to-consumer model. But I think it has real value for data science. And so, because it can really help us standardize our data engineering workflows. It's a well-documented specification where canonical data is stored in a really consistent location throughout the spec. So for example, here's a procedure resource. And the procedure resource has a subject key, which is who the procedure was performed on. It also has a key for the code, which is the identification of the procedure. And we would like it to be a SNOMED CT ontology that describes that. And there's just one of them, and it's a codable concept. The nice thing about that is that we don't need a data analyst to work hand in hand with our programmers to understand the data to build applications on top of the medical record. One organization that we've worked with had a very large, their medical record had a very large Oracle schema. All the tables were 8 characters long and all caps, of course. And the knowledge built into that schema to get the data out we needed to create clinical applications was very, very deep, right? And you don't want that to impede every one of your developers' experience in accessing data to build applications. Another great use of FHIR is to normalize variability from data sources. So whether you're combining legacy data sources or you're combining the data warehouse with a real-time store, you can use FHIR and its model to just normalize the data input and have a consistent data engineering workflow. Like I mentioned, creating structured registries from FHIR is really valuable. Of course, in the healthcare APIs, you can dump directly to BigQuery. But as most people working in the field know, a lot of value is in unstructured data in medical records. And so working with health systems, we've found that there's a lot of value in writing very small, targeted programs that leverage natural language processing or parsing, multiple ways where you can just write these ad hoc programs to create highly structured and really valuable data sets. So now that I've told you why FHIR is so great, let me tell you why scalable FHIR implementation is difficult. The specification is really a deeply nested data structure. And when you try and model this relationally, you end up with hundreds of tables and thousands of foreign keys. And if you try and lay an ORM on top of this, you can quickly overrun the database's capacity to do select queries because of a lot of that deep backlinking. The spec also, these references between this graph of medical record models is essentially a generic foreign key. And so you have a ton of generic foreign keys, which again is really hard to deal with at a scalable implementation level. So we were actually talking about building a FHIR on top of Spanner when I came across the Google Healthcare APIs. And what's great about this is that they already did it for us. It's a standards compliant HL7 implementation. And so essentially, we can just drop this into any of our previous FHIR implementations. We don't have to take something off the shelf, manage the index size, manage the database size. It's fully managed and high scalability. And this is just an example of how I think that platform as a service for healthcare can really accelerate it, right? We're not doing the nuts and bolts of building our infrastructure. If we step back and look at imaging in healthcare, I think imaging is interesting because it's one, it and genomics are one of the few high-dimensional data sources in healthcare. So that's where we can really extract insight with machine learning. So of course, we can label our images and build a classifier. In this case, it would be in mammography. And we can take TensorFlow off the shelf. We can train a model, and we can spin up a TensorFlow server or use ML Engine to serve our model. And off we go. But the problem is that data sets in healthcare are small. There's not a lot of health information exchange. There are no national aggregations that are widely accessible. And so transfer learning is really key in healthcare. If you're not familiar with what transfer learning is, especially in the context of images, it's where you kind of stand on the shoulders of a previous convolutional neural network. And then you tack your model onto the end. And so what's encoded over there, say like Inception v3 from ImageNet, is what are the features of an image generically? Can we take millions or billions of images and do line detection, feature detection, and then we'll just tack our model onto the end of it Again, we'll stick our huge team of data scientists inside our health system onto that model and then deploy it. But as you guys probably guessed, there's not a huge team of data scientists at every health institution. So how do we do this quickly? How do we iterate and leverage machine learning on this high-dimensional data? For us, we found a lot of value in AutoML Vision. So AutoML Vision automates that whole process for you. You don't need specialized TensorFlow knowledge to be able to train a model on your DICOM images. The DICOM API also does a nice thing, which is transcode your DICOM images into JPEGs, which you need to do for training. And then once it trains and you find the right level of sensitivity and specificity, it automatically deploys your model for you. So now that we have our tools together, we're going to use the DICOM API for images, the FHIR API for our FHIR store. We use Cloud SQL for our registries. You could also use BigQuery and AutoML Vision. Let's talk about how we're actually building this in an architectural level. So this is work that's in progress at the Sun Yat-sen now. And if you've ever built an ETL on healthcare data, you know that it's a real challenge. You want it to be very robust. You don't want to have missing data. And so how you do that can be a little bit tricky. Our opinion is that you want to write once and succeed. You don't want to have a chatty API. You really want the rate limiter to be your internal system. And in this diagram, I'm going to use blue arrows to denote a pub/sub asynchronous message queue, just for clarity. So let's say we write a FHIR resource into cloud storage. It kicks off a message into a pub/sub. And the nice thing about asynchronous message queues is that you'll get durable delivery, right? It's at least once delivery. But at least once means that it's maybe twice or maybe 3 times. So we'll leverage cloud data flow, which will give us exactly once delivery. And that's where we'll write our deduplifying application. We'll leverage the FHIR specs use of identifier to query the FHIR API, for example, for this patient and say, hey, do you have this patient with this MRN? If so, create it, or if not, create it. If so, update it. And similar for the DICOM store. From there, when we create that resource in the FHIR store, that kicks off an asynchronous message that Cloud Function consumes and updates the registry. And I can't emphasize enough how important having a living registry is that's constantly being updated. That is a huge value for a health system, both in retrospective and analytics, and also for machine learning. So now that we have all of our medical record and our images in, we can use the FHIR store and the registries to create a training, test, and validation data set, hand that bulk over to AutoML Vision, and have it train a model. So now we're all ready to go. Let's say a new FHIR resource comes in through the API, or in this case, a new image lands in the DICOM store. Again, we get an asynchronous message that is consumed by a Cloud Function that will actually run our model and deliver it. So we use the Cloud Function to look into the registry and select appropriate models for this patient and for the image type. We then run that model in AutoML Vision, and we use an asynchronous queue to deliver it back to the health system's EHR. That's surfaced clinically in the workflow. And what we have built here is an entirely serverless system that is easy for us to iterate and create new clinical decision support products on. And we just have to essentially do that upfront investment in ETL. So what we found that the key to successful innovation is that you need to have a SaaS cloud workflow, right? You can't do everything yourself. And if you can make a secure workflow that allows you to access these cloud tools, all of a sudden now, number 2, you can move fast with these platform as a service things that I've been talking about. You're not reinventing the wheel. You're not running a database. You're not taking a FHIR store off the shelf. And so now that you can quickly create healthcare-specific applications, you're able to leverage your expertise in-house, right? The hard work is to empower individuals in your organization to solve clinical problems and without specialized skills to really improve the patient experience and health system operations.